All right, and we are live. And once again, happy to present Misha Kornev, who will tell us about the coarse homology theories. Please, Misha, take it away.
Yeah, thank you. Today will be the last lecture about this stuff, and we will talk about examples of coarse homology theories, and we start with the first section. So it will be called forcing U continuity, and this section will be about the way of how to obtain homology theories from the functor E from Born-Coarse to some complete stable infinity category. So C is a complete stable infinity category. And it turns out that we can construct a new functor which will be U continuous. So we can form the functor EU from Born-Coarse to C. And by definition of coarse homology theory, this will be indeed some homology theory, and usually we want to require that this usually the map from EU to E is an equivalence, usually. And it turns out also that if E is if for the functor E we have an excision and it vanishes on Flask spaces or some properties like this, then the functor, if E is good, then EU is so EU. Okay, and one can expect that this functor EU, continuous functor, is of the following form. This is just the colimit over U over all entourages living in C, and this is colimit of E of XU. And recall that by definition on U continuity, you should have the following relation. So colimit over all such terms should equal the functor applying to whole object, to whole Bornological coarse space. So we can construct the resultant value. So we can start the value from different pieces, different restrictions. Okay, and this definition can be applied in the setting of so we can apply this definition to object only, to objects only. So we want to have a functor. So So there is a problem now. What's happened? I don't understand.
We can see your screen right now.
Yeah, but on my computer there is no connection, and I try to connect. Yeah, just a second. Yeah, okay.
Recording in progress.
Sorry. Okay, now I continue my talk. So we can define this EU on objects only, but not only on objects. It can be defined via the following construction. Also for morphisms. So we want to define a category. Category born coarse C, and objects are pairs XU, X from born coarse, and U is an entourage. And morphisms will be of the form, so morphisms between pairs X U and X prime U prime, where F from X to X prime is a morphism in the category of Bornological coarse spaces, and such that the following holds: F times F of U should contain in U prime, and the morphisms look like this. Okay, and we have the following functors from this category. Sorry, born coarse C. So two forgetful functors. The first one. So if you have a pair XU, you can forget say yeah, you can restrict your set of entourages, and you get the space XU, and it will live in born coarse, of course. And the second forgetful functor maps this pair to X, just forgetting U. Okay, and now consider the following diagram. So having these forgetful functors, one can form the following diagram. So we take this forgetful functor P, form and we take the composition between E and Q, just the composition between our functor E and the forgetful functor Q, and we can form the following left can extension. Yeah, and to the category C, we can form the following left can extension, and we will call it. It will be called EU by definition. It equals LAN. This LAN. Yeah, and of course our functor E maps Born coarse to C. So we have the following arrow, and by the universal property of left can extension, we have the following. We have the following property that. Notice that we have a natural transformation from Q to P. So just you have Q of XU, and it is XU, and it maps to X. It's mapped to X, and X is P of XU. So you have the following natural transformation. And applying E, we get the following natural transformation from E composed with Q to E composed with P. Yeah, so we get the natural transformation from this arrow E composed with Q and with this one, and it can be decomposed via the universal property of the left can extension. Okay, and now we get the natural transformation from EU to E. We get EU to E. And the pointwise formula for left can extensions gives us the following isomorphism. So EU of X can be identified with the co-limit of the composite over the category. Yeah, and note that the subcategory of consisting of objects X, U, and identity on X is cofinal in the category, in this over category. So is cofinal in Born coarse C over X. So recall that being cofinal subcategory means that you have a cofinal functor. So the functor, the inclusion functor of this, the inclusion functor is cofinal. It means that if you take a colimit, so if you take say colimit F. Your inclusion factor I, iota, and the set valued functor, some set valued functor, then the colimit doesn't change in this setting, so you can remove this iota, and it will be true. Yeah, and this is the notion of being cofinal subcategory, and so yeah, and this condition is equivalent to the fact that Born this over category is connected. So it means that any two objects can be for any two objects, there is a path consisting of arrows or just a zigzag between any two objects. It means that this category is connected, and it is equivalent. So zigzags, and it is equivalent to the fact that it's that's all. It means that we get an isomorphism. So the fact that this subcategory is connected means that we get the following isomorphism: EU of x and colimit of E of xu over u sitting in Cx. This is a easier corollary of this statement. Okay, and now the proposition. The following properties are inherited by EU. So the following properties are inherited by the functor EU. So coarse invariance. The second one, excision. And the last one, vention on Flask Bornological coarse spaces. Oops. Vention on Flask Bornological coarse spaces. Let's verify these properties from this construction. Proof. So proof the first property. Let E be coarsely invariant functor. Then we should verify that EU of this object, this Bornological coarse space, to EU of x, this is an equivalence. Where on these two elements, on this set consisting of two elements, we consider the maximal Bornology and maximal coarse structures. Maximal Bornology and the maximal coarse structure. Okay, note that we have the following isomorphism between this 0, 1 cross x restricted to U bar, where U bar is the Cartesian product of 0, 1 squared to U, where U is an entourage living in Cx, and it is isomorphic with the 0, 1 cross XU. This is obvious, and it means that we have the following chain of isomorphisms. So just apply our E and get 0, 1 cross X to U bar is equivalent with the this. And so it follows from the equivalence above. And the second isomorphism with the XU, it follows from the fact that E is coarsely invariant. So we suppose that E is coarsely invariant, and we should verify that EU as well. So as U is coarsely invariant, and so we get the desired isomorphism. Not now, but soon. So from the cofinality of this family is cofinal. It means that we can consider the colimit over U, over general U, or over this U bar, and the result will be the same. So this colimit is isomorphic with this one over U bar. And now we know that the latter is isomorphic with this guy. Okay. Well, we're done at this point. The second point. So suppose that E is coarsely invariant, and and for E we have the property of excision. Then we should verify that EU also have this property, but I'll omit this proof. So complementary pairs on X are also complementary pairs on the restricted X. So if you have a complementary pair on X, then it will be, of course, a complementary on X with the restricted with the C generated by only U. So it is obvious, and suppose that suppose that E vanishes on flask spaces. So suppose that let's X be a flask space, and F from X to X is a map implementing this flatness. And consider the following sets: V, F times ID, applying to which is applied to diagonal on X and W so okay, I think I can skip this proof. So some technical details are not interesting. Okay, so corollary here. Assume that E is coarsely invariant. E vanishes on Flask spaces. And E satisfies excision. Then the functor EU will be, so EU is a coarse homology theory. And the second point is that if E is a coarse homology theory, coarse homology theory, then it follows that EU to E will be an equivalence. And the last point, if the coarse structure is generated by a single entourage, if CX is generated by a single entourage, then this natural map from E of X to E of X is an equivalence. So recall that this is the case in the setting of path spaces, path metric spaces. So there we saw that the core structure can be generated by the only entourage. Okay, the next section. Additivity and coproducts. Suppose that E is a coarse homology theory. So for E, the properties like excision, vanishing of Flask spaces, U continuity, who holds E a coarse homology theory, and C is is complete. Definition: E is said to be strongly additive. Strongly. If for any family of Bornological coarse spaces Xi, we have the following equivalence: E of the free union of xi's is equivalent to the product over I of E of xi. And the next definition, E is just additive. If for any I and I, for any set I, the following holds just for the one pointed set space. So we have the following equivalence. And the following lemma describes the fiber of the natural map. So lemma. If you have a coarse homology theory E and this family Xi, some family of Bornological coarse spaces, and suppose that E is strongly additive, then there exists a fiber sequence. The fiber, it will be a fiber, the direct sum of E of xi's. So this sum is taken in the category of stable infinity category. Infinity categories, yeah. It will be a fiber, and a fiber of the map of the following map. Where I is in I without J, and J is finite subset of I. So it means that we have the following fiber sequence. Let's prove this lemma. So we have canonical maps. We have canonical maps from E of xi to E. So these maps are induced by just the inclusions of xi to the mixed coproducts or just coproducts xi or xi into mixed one, and you just you should apply this functor E, and consider the coproduct over all I or all I's, and you will have these maps, the first one and the second. Okay, and it can be shown that the fibers of the maps belong to the category. Oops, sorry. Belongs to the fibers of the maps belong to a category as of spaces generated by a discrete. So I'll explain the notations. So A is a set of objects in Born Coarse spaces. A is a set of objects. A family, a set of objects in Born Coarse. This sp chi of A denote the minimal co-complete stable full subcategory of motivic Bornological spaces containing E of A. So this denotes the minimal co-complete stable full subcategory of sp x fancy x containing containing E of A. And a disk, the set of discrete Bornological coarse spaces. Discrete means that the set of entourages generated by empty set, or just this set contains only subsets of the diagonal. The set of discrete Bornological coarse spaces. Okay, and now consider the case of mixed unions only. So in this case, X will be just the mixed union of X size, and recall that E of X, but by definition, not by definition, but from the by definition of E, it will be the co-limit over all entourage U in C of U of X restricted to U. And suppose that U contains the diagonal, and in this case there exists a finite subset G, subset of I, and entourage Uj in Cj for any J in J, such that U can be decomposed, can be represented as the union of Uj's from J and the diagonals of X size. So we suppose that U contains the diagonal, and as C generated as this set of entourages is generated by entourages living in CJ, but we can form only finite unions, and it means that we will have only finite union of UJs, and the other will be just the diagonals of Xi's. Okay, now we can restrict along this U our X. So we get that XU will be isomorphic with this union XJ restricted to UJ, and Xi restricted to the diagonal of Xi, but we will denote it by Xi disk. So by definition, it will be Xi disk, this discrete. And so we apply our functor E to this isomorphism, and we get E of XU will be isomorphic with the following coproduct in the category of stable infinity categories. Yeah, E of XJ UJ plus E of this union I in I without J. Okay, and by excision we get the following isomorphism. So E of Xi discrete over I in is an I without J mixed will be isomorphic with so we can subdivide this so we can represent this set of indices. Just we take the subset J prime, subset of indices, which contains the set J, and now the set of indices I without J can be represented as the union of indices I without J prime and I and J prime without J, and it will give the following isomorphism. Okay. And it means that we can restrict or project onto this summand, the first summand. And so we did it for the aim that we want to form the colimit over J and over U, or over indices J, the set of indices J, and over entourage U. These repeated colimits, and taking these repeated colimits, applying this to this isomorphism, we get the desired Faber sequence. So we get, so applying it to this one. Yeah, this sum is taken over J, sorry, J in J, and so we can take colimit over UJ, and after that we can apply a colimit over J, the set J, and as we have this splitting, we can organize this splitting into the exact sequence. Sorry, fiber sequence in some sense. So we get the sequence E xi to E of x to the remainder j is finite, E of mixed xi discrete. Okay, and the fiber of this map in turn will be sigma inverse of R, where R will be this expression. Okay, and this R is in category SP X of a discrete. Okay, and now in the same manner, one can prove the same result for not mixed coproduct, but for just coproduct, and definition here. Consider coarse homology theory E, and we say that E preserves coproducts if the following natural equivalence holds. So E of xi over I is mapped to E of the coproduct over I. So this is an equivalence. And from the fiber sequence above follows that coarse homology theory preserves coproducts. To prove that, to verify that it is so, it suffices to check that this holds on for discrete Bornological coarse spaces. So, okay, to verify this condition, it turns out that it suffices to verify it for discrete Bornological coarse spaces. Okay, the next section is about coarse ordinary homology. So the first definition of coarse ordinary homology is by Bloch and Weinberger. So suppose that denote by this the small category of very small chain complexes. This is the category of small just small chain complexes, and objects will be, as usual, chain complexes, and morphisms are chain maps, and the target category of the desired functor hx. So hx will be yeah. So the target category of this functor, this homology functor, will be the category, the infinity category of the stable infinity category, which is the localization of the category of chain complexes in the set of quasi-isomorphisms. And recall that there is a functor L between the localization functor from the category of chain complexes to this localized category. And we will use this Dwyer-Kahn localization functor. Okay, and the homotopy category of this category is just the unbounded derived category of abelian groups. So here is the category of abelian groups, and this category is stable, very small, complete, and co-complete. Now define a functor Cx from the category born coarse to the category of chain complexes. X will be mapped to the chain complex of locally finite controlled chains. The chain complex of locally finite controlled chains. Now I'll give some definitions which can be found here. So some definitions. A point x0 xn in xn plus 1 meets B if there exists an index I in the set of in this set such that xi is in B. The next definition, let U be an entourage of X, and we say that this point x0 xn is U controlled if for any I and j the pair xi xj is in U. The next definition, we say that the map from xn plus 1 to z is an n chain on X. Just a function. If it is sorry. Sorry. It's okay now.
It's still showing because they actually write that.
Yeah.
So their constraint is that this term, this
It's
is
okay.
this C,
Can you hear me?
and this term is that swap.
Uh-huh.
And so if you look actually later right now.
So should I repeat something?
Yeah, maybe just these last two lines.
Yeah. So I'm
Uh-huh,
saying like
um,
those,
Yeah.
like this at far.
Okay.
Right
Now I introduce some definitions and notations. We say that if we have a point x0, xn, and in xn plus 1, and we will say that this point meets B, if there exists an index I such that one of these coordinates is in B. U, the entourage, some entourage U, consider some entourage U, and so we will say that a point is U controlled if for any indices I and J, the pair xi and xj is in U. We say that C, the map C from xn plus 1 to Z is an end chain, is this is just a function. So the support of this C consists of all points x for which C of x doesn't vanish. Okay, and consider X is a Bornological coarse space, and U is an entourage, and C is end chain. Then C is locally finite if for any B for any bounded B, the set this support the set of the set which the subset of such points of the support which meet B is finite. Okay, and we will say that C is U controlled if for any point in the support if any point is U controlled. Any point of the support is U controlled. And now we are ready to define the desired functor. Define Cxn of x to be the abelian group. Of locally finite and controlled end chains. So these conditions we require for the purpose that the next sum has some sense. So we can form this infinite sum in general, C of x times x over all x living in x and plus 1 and chain. And we can define the differentials just by definition di of x0 xn will be x0 xi skipped xn. And we can extend this di linearly, and we get di defined on cxn to cxn minus 1 of x. And now define just d as the altered sum of di. And one can check, as usual, that the square of z equals 0. So we get we get a chain complex consisting of cxn's and the differential z. And this is a functor. So if you have a map of Bornological coarse spaces, then you get a map between you get a chain map in the natural way. And now we are ready to define the desired functor of ordinary Bornological ordinary coarse homology functor. So we were ready to define it. So this functor will be from we will map from Born coarse to the category of chain complexes. So this is it will be the composition of Cx and the localization functor L. And now there is a theorem so this theorem tells us about the fact that this functor is a SP valued coarse homology theory. So we should verify that this functor is coarsely invariant, the first point. The second point, that this functor satisfies excision. The next point is that it vanishes on Flask's Bornological coarse spaces. And also, this functor is U-continuous and strongly additive, and also preserves coproducts. So we should verify these things. Now we will prove this theorem by 5 or 6 steps. So the first step, proposition 1. Hx is coarsely invariant. Okay, so suppose that proof. Suppose that f and g from x to x prime are close to each other. And in this case, we should show that hx of f and hx of g are equivalent. And for that, we construct a chain homotopy from construct a chain homotopy from Cx of G to Cx of F. Okay, now suppose that I is an index. Take some index and consider the map hi from xn plus 1 to xn plus 2. This map increases the degree, and it maps x0 xn to f of x0 f of xi, g of xi, g of xn. And the condition of closeness is used to verify that hi can be linearly extended, and this map hi induces the map hi on chain complexes, and the condition that f and g are close to each other means that for any I and j, you have that f of xi, this pair consisting of f of xi and g of xj is in U, living in Cx. This is the correct definition of hi. Now we can define the map H just as an altered sum minus y I multiplied by hi, I from 0 to n. And one can check that this is the desired chain homotopy. So we get the following quality. And so we're done. So okay. Of course, we should apply after that the functor L, but it is, but it's obvious that we are done here. The next proposition. The functor hx satisfies excision. Proof this. Suppose that we have a Bornological coarse space, and zy is a complementary pair. Then hx of y by definition, is the colimit of hx of yi over I, and in turn, it is the colimit by definition of LCX of yi. And we can use the property of the functor L, and we can move it here, and we get L colim of CX of yi. Now, notice that the functor, the chain functor CX maps an injective map to the injective one, and it means that this chain complex can be interpreted as a union of some complexes in X of X. So we, in particular, we have the following inclusion: CX of Z into CX of X, and form the following diagram. So we consider the following short exact sequence: Z intersected with the Y and embedded into CX of Z is mapped to CX of Z, quotient by CX of C cap Y is mapped to 0, and also it is embedded to CX of Y, and it is embedded into CX of X. And here we have an inclusion, and here we have the quotient of abelian groups. Yeah, and we should oh, so sorry, here we just have an arrow, and we should verify that this square is the push-out square. And to do this, it's sufficient to prove that the right vertical map is an isomorphism. So verify that the right hand side map is an isomorphism. So injectivity. Verify the injectivity condition. Suppose that C is in CX of Z. So we take C from here, and we suppose that this C is mapped to 0. C is mapped to 0. Yeah. Then in this case, C is in intersection, as we have the fact that it is mapped to 0. Then sorry, we have of course C from here, but we should consider the class of C in this abelian group. So we would take this C and map it at 0, and then it follows that C is in intersection of CXY and CXT, CX of Z. So if we have here we have 0 in this group. So if it's so, then we are in this intersection. Okay, but this intersection, of course, is the same as the CX of the intersection of Y and Z. And it means that C is a trivial class, has a trivial class in this group. So the class of C is trivial. Surjectivity. So sorry, I'll continue now. Can you hear me?
Yes, we can hear you.
Okay, so I just use my iPad and on only this. Okay, so what's the point I should say again? What's
Yeah, I think everything was audible just before.
Okay. Now surjectivity. Surjectivity, but of course, it's it isn't it's technical, so I just skip it. And now the next proposition is about Flaskness. Yeah, it's about Flaskness. If X is a Flask, Bornological coarse space, then Hx of X is isomorphic to 0. Okay, so I briefly schematically prove this proposition. So suppose that F implements Flaskness on X and define the following map S from xn plus 1 to cxn of X via the formula X is mapped to Cx of Fk of X over K over such K. And one can check that this S extends linearly to a map, to a chain map. So S can be extended to a map from Cx of X to Cx of X. And from the definition of Flaskness, one can derive that S is good map. The map S is good. So S takes value in locally finite chains, and S maps control chains to control chains. It can be derived from the definition of Flaskness implemented by F. And in this case, one can note that identity plus this will be S. So you when you apply F, to this sum, of course, you should add this guy. And in the case, after doing that, you get the original map S. And so we have this this relation, and apply an L, we get the following relation: identity on hx of x plus hx of f composed with L of s is isomorphic with L of s. Yeah, but we know that f is close to identity, as this is from definition of being flaskness, and f is close to identity, and it follows that hx of f will be identity. So this is identity, and we can remove this L of s from the both sides, and we get that yeah, and we get that hx of x will be isomorphic to 0. Now the next step, hx is U-continuous. So by definition, hx of x is L of the colimit of Cx of x restricted, and from the property of L, one can move this L and apply to Cx of xu, and it will be the colimit of hx of xu. So we're done. Hx is also strongly additive. It's easy. I'll omit the proof, and hx preserves coproducts. Consider an example. Suppose that X is a set considered as a Bornological coarse space with the maximal structures. So with the maximal structures. Then hx of x will be isomorphic with the L of z. So it means that this theory is not trivial. Okay, I have So I can skip some topics, and the last section will be about equivariant theory. Equivariant ordinary theory. So, as in the case of ordinary coarse homology theory, we can introduce the equivariant theory, ordinary theory, and for doing that, we form a subcategory. We form so firstly consider a category consisting of Bornological coarse spaces with a G action. And in this category, the category G-born coarse space sits, and this category, this is a subcategory consisting of this is such a category that the set of G invariant entourages, so CG, is cofinal in C with respect to the inclusion relation. So consider the example. Suppose that G acts on the metric space XD as isometrically. Then we get the metric space XD in Born coarse, G-born coarse. Indeed, any entourage is G invariant. So recall that we consider here the natural Bornological and coarse structures, and the set of entourage is generated by the set consisting of points distance between which is less than some delta, say. And of course, this action is as this action is isometrically, as we have isometric action, then of course any subset, any entourage will be G invariant. Another example. Another example. Suppose that Z acts on the real line with the usual metric by the rule nx is mapped to the power n multiplied by x, and there are no invariant entourages. And this is an example. This is an anti-example in some sense. Okay. The next important example is about Riemannian manifolds. So Just a second. Just a second. Okay. So, example. Consider Riemannian manifold, say M, with the metric G, and we can form the Bornological core space M D G S G, where so this Bornological core space is important in the setting of Dirac operators, in index theory of Dirac operators. And the Bornology B SG is a larger one. And
Misha,
yeah.
can you explain a little bit what is a Dirac operator?
Say again.
Can you explain a little bit to elaborate what is a Dirac? You said this example is relevant to Dirac operators.
Okay.
And because I'm a physicist, so I want to know if there is a correspondence with what we call a Dirac operator in physics. That's why I want you to say a little bit more, if you can.
Okay, I can. I'll try. Okay. So yeah. It turns out that you can define the coarse index, and it will be and there is a connection with this coarse index with the usual index in index theory. So there is a relationship between them, and and yeah, I'll try to explain this connection, but firstly consider now consider this example. So we can introduce the Bornology BSG consisting of such subsets of M, for which there exists K compact subset of M, such that infimum over B without K of SG is positive. And we get this Bornological core structure. And now, okay, now I'll try to explain the connections between index theory. Just a second. Okay, so so there is a connection. There is a connection between the index of equivariant Dirac type operators on complete Riemannian manifolds with the proper action of group G by isometries and the equivariant coarse K homology. So assume that M admits an equivariant spin structure. Assume that M admits an equivariant spin structure. It means that, for example, you have a spin bundle, or you have a bundle of Clifford algebras or something like that. But okay, and yeah, assume that we have the structure, and let D the associated the Dirac operator, the associated Dirac operator. So Rho observed that there exists a notion of index of coarse index. So he introduced the coarse index X of this operator, and the value of this index is in K K theory, coarse K theory, KXG in G invariant of dimension minus dim of M with the Bornological core structure DGSG. Sorry. SG is the scalar curvature. Of course, I should mention this moment. Okay, and this index takes values in the kx of M. So I should define this guy, but yeah, and I can try to do it. So this functor k chi g by definition is the composition of functors k and the functors vg, where vg is a functor from Bornological core spaces to C star categories. Vg from G-born cores to C star category. So C star category is a generalization of the category of C star algebras. And yeah, so just a second. Suppose that X is a G Bornological core space. And we can form yeah, and we say that we have a X-controlled Hilbert space, X-controlled Hilbert space. So is a triple consisting of a Hilbert space, a unitary representation of group G. So R is a representation G in Hilbert space, and mutually family, mutually orthogonal finite dimensional dimensional projections. So P are projections which are mutually orthogonal. P is a family, Px indexed by points of X, such that the sum of these projections is the identical morphism, and some additional details, but we'll skip it. Okay, and we can form a control morphism between X controlled Hilbert spaces. So if you have a control X control morphism, X control Hilbert space X rho P, and the other, then you can consider the operator A between them. So this map consists of an operator A from H to H prime, and such that the following holds for any J and J, and some technical conditions, and one can denote by C star between these spaces the closure in BH prime of the set of controlled morphisms. So we can close the set of all control morphisms, and we get this C star, and so we obtain a C star category Vg of X. So Vg of X is a category consisting of X controlled Hilbert spaces morphisms are these elements of C star, these operators between H rho P and H prime rho prime P prime. And the involution given by taking the disjoint, just the usual involution. And okay, and we so we can form the C star algebra. Definition. Suppose that X is itself is locally finite, and rank of Px equals 0 for any X. Then one can form the endomorphism C star algebra. So C star of H rho P by definition is endomorphisms over Vg of X, this, and is called the equivariant uniform rho algebra associated to X. This is a rho algebra, C star rho algebra associated to X. And if you have a map in the category of Bornological coarse spaces, then you have a functor Vg, and it will be it will map F in the following way. So if you have a H rho P, then you can map it to H rho F star P, where F star P by definition is the sum over sum of projections where X is from the fiber of for fiber over X prime. Okay, and now after the definition of VG, so we get a functor from Bornological core spaces, J Bornological core spaces, to the category C star category, and we can combine it with the spectrum valued K theory functor K from the C star category to the category of spectra. And in this case, we will obtain K coarse K theory equivariant just as a composition between K and V J from G-born coarse to the category of spectra. And this construction coincides with the raw construction, original raw construction in the setting of proper metric spaces with isometric group action. So, for example, in the case of Riemannian manifolds, now in the setting of the index theory, we observed that one can construct an index x of z. Where is it? Yes, this index, and it will take values in kx in these objects in this object, and okay, and if G is trivial, so if G is trivial, then and suppose that the scalar metric scalar curvature admits a uniform positive lower bound, admits uniform positive lower bound, then outside of compact subset, then then this operator is Fredholm, and its Fredholm index so just denoted by index of Z is in usual K theory of dimension dim of M of C. This index can be derived using the functoriality of the coarse K homology in the following way. So index of Z equals P star of the coarse index X of Z. Yeah, and so P star is an induced map used by the projection, I suppose, and we use the fact that if we take this K theory of a point, then we get the usual KU theory. Sorry, P here is the map from M to a point, and we take the direct image of this index, and we get the usual index, the usual Fredholm index of this operator. So, and this relation is so this relation motivates this theory in particular, I suppose. But of course you can. So I recommend you to find some articles by Rohr or this or the Bunke, and I can give some references. So if you want, but yeah, this is all. So I have no time, and I should skip some moments, but I think that we can end our seminar at this point. But
All right.
Thank you for the question. So I guess that my abstract answer was fruitful in some sense. I don't know, but anyway, thank you.
Thank you, Misha, for this wonderful talk. Once again. So if there are any questions, please ask them now. There are no questions. Let's thank the speaker.